The Annihilator Approach is another approach that is used to solve non-homogeneous equations. Of course, the superposition approach is quite effective, but the Annihilator Approach is more solid in the sense it is a nice process based on the differential operator. So a non-homogeneous equation of nth order is given by an x, y raised n, the nth derivative, an minus 1x, n minus first derivative, all the way up to a1x, first derivative plus a0x times y equals some function g of x. Now, d is called the differential operator. It is a very common operator that is used in engineering, and it is used in mathematics, especially in the field of differential equations, difference equations. It even shows up in time series. So the purpose is to rewrite the equation in terms of the differential operator. So by the form that I wrote, it should be obvious that d raised n times y would give us the nth derivative d raised n minus 1 times y would give us the n minus first derivative, all the way d raised 1, or d, of y would give us the first derivative, y prime. So the key here is we can make use of the differential operator, and you could see that y is common in all of these terms. And we can pull that y out. So we could simply rewrite the given differential equation using the differential operators. So that expression is, I believe your textbook calls it as L, so I'll use the same notation, L. And that entire expression for L would form a nth degree polynomial with constant coefficients. We would like to have constant coefficients. If you observe closely, I'll put it as a remark, if d is replaced by m, the polynomial simply becomes the auxiliary equation. And you may say, well, what is the purpose of the Annihilator Approach, and why do we even call it the Annihilator Approach? So the non-homogeneous dE can be rewritten L times y equals g of x. So the first part, L, is simply that corresponds to the original dE. The objective here is if I apply another operator, let me just say LP, the goal is to apply another operator or another expression containing the differential operators so that g of x becomes 0. In other words, if I took L1 and I apply to L of y on both sides, L1 should make g of x 0. So, in other words, L1 annihilates g of x, and hence the process is called the Annihilator Approach. It sort of kills off gx and we end up getting 0. So, L1 is called the Annihilator Operator because it makes g of x 0. Now, why should we make g of x 0? So, the equation, the non-homogeneous equation, L of y equals g of x, after the application of the annihilator operator becomes a homogeneous equation in the sense L1 of L of y would simply be equal to 0. And we know, solving a homogeneous equation, it's pretty straightforward. Once we find this, we can solve for the arbitrary constants, and if we want, we could find the particular solution. So now we'd like to know or identify the correct annihilator operator for a given expression. So we'll start simply with a polynomial. Suppose we have x raised n as the expression. Then when we apply the derivative operator, this should eventually become 0, and that is the goal. So we need to find what that operator is. So if I start with x, the first time I applied the differential operator, I get 1. The second time I apply the differential operator, I get 0. So the differential operator gets applied twice, d followed by d, so the annihilator for x is d squared. So if we start with x squared, the first time we apply, we get 2x. Second time we apply d, we get 2. Third time we apply d, I get 0. So the annihilator for x squared is d cubed. Let's say we have 6x raised 4. The first time we apply the derivative, we get 24x raised 3. Second time we apply the differential operator, you get 72x squared. Third time we apply the operator, we will have 144x. Fourth time we apply the operator, we get 144. Fifth time we apply the operator, we get 0. So the annihilator for x raised 4 is d raised 5. So in general, d raised n plus 1 will annihilate expressions 1x, x squared, all the way up to x raised n. Or if you want to write it in a different way, d raised n will annihilate expressions 1x, x squared, all the way up to x raised n minus 1. So you may ask me, why all of these? Well, I know that d cubed will annihilate x squared, but d raised 5 would also annihilate x squared, because past d cubed you will get 0 and you're simply differentiating 0. So d raised 5 not only annihilates x raised 4, it also takes care of every single exponent below that. In other words, x cubed, x squared, x, and a constant, which is why we say that d raised n will annihilate all expressions all the way up to x raised n minus 1. If we have an exponential function e raised alpha x, so e raised alpha x is annihilated by d minus alpha. For example, consider e raised to x. My argument is e raised to x will be annihilated by d minus 2. So let's see if it holds true. E raised to x, d minus 2. So I'd have d minus 2 e raised to x, which should be d e raised to x minus 2 e raised to x. The derivative of e raised to x is 2 e raised to x minus 2 e raised to x. We get 0. So clearly, d minus 2 annihilates e raised to x. In general, d minus alpha will annihilate e raised alpha x. There are derivations for this, but let's not get into all that. I'll just write the general form. So in general, using the previous property and the current one, d minus alpha raised n will annihilate expressions 1, oh, not 1, meant to say, e raised alpha x, x e raised alpha x, x squared e raised alpha x, all the way up to x n minus 1 e raised alpha x. The same logic as we had in the previous case with the polynomial case. A higher order operator will annihilate everything below that. So we're just extending that to an exponential function. Next, we have the complex case where we would have sines and cosines. So trigonometric functions, so again, this involves a derivation. I'm skipping that. We can verify by applying this operator to e raise alpha x cosine beta x and e raise alpha x sine beta x, and certainly it will become 0. So d squared minus 2 alpha d plus alpha squared beta squared will annihilate both e raise alpha x cosine beta x and e raise alpha x sine beta x. Now, if alpha is 0, we can readily see that d squared plus or minus 2 times 0 times d plus 0 squared plus beta squared, which is d squared plus beta squared, will annihilate alpha is 0, e raised 0 is 1, so cosine beta x and sine beta x. So trigonometric functions such as sine and cosine can be annihilated by d squared plus beta squared. Now keep in mind, this doesn't apply to logarithmic functions, rational functions, or tangent functions, unless we could rewrite it in some nice way. So this only applies to cosines and sines. What if we have a polynomial multiplied to a cosine and sine? The golden rule of thumb here is d squared minus 2 alpha d plus alpha squared plus beta squared raised n will annihilate e raised alpha x cosine beta x, e raised alpha x, x cosine beta x, e raised alpha x, x squared, cosine beta x, all the way up to e raised alpha x, x raised n minus 1 cosine beta x, and applies to sines also, e raised alpha x sine beta x, e raised alpha x, x times sine beta x, e raised alpha x, x squared times sine beta x, all the way up to e raised alpha x, x raised n minus 1 sine beta x. So using the same logic, we can, like we used over here, we can conclude that d squared plus beta squared raised n will annihilate cosine beta x, x cosine beta x, x squared cosine beta x, all the way up to x raised n minus 1 cosine beta x, and sine beta x, x sine beta x, x squared sine beta x, all the way up to x raised n minus 1 sine beta x. So here is an example where we have to write the given differential equation of the form L of y equals Q of x, where L is the linear differential operator with constant coefficients. So if possible, we've got to factor L. So g of x is sine x. Now I could write y double prime as d squared y, and y is simply y. There is no need to take the derivative. So if I pull y out, I would have 9d squared minus 4 multiplied by y sine x. Could we factor 9d squared minus 4? Yes, we can. We can factor it as 3d plus 2 and 3d minus 2 y. And that is simply L of y, and that is g of x. Here we have another second order differential equation, and we would like to write it in terms of the differential operator, and if at all possible, we would like to factor it and write it in terms of the factors. So y double prime is simply 2d squared y prime is 3dy, minus 2y equals 1. So I could pull y out, 2d squared minus 3d minus 2 times y equals 1. And would we be able to factor this? I believe we can. I could write it as 2d squared minus 4d plus d minus 2 y equals 1. If I pull 2d out, I have d minus 2 plus 1 times d minus 2, which should give me the factors d minus 2 and 2d plus 1, y equals 1. So L of y is simply d minus 2 times 2d plus 1 y, and g of x is simply 1. Earlier, I made a remark that the auxiliary equation is closely related to the linear differential operator, in the sense, if we had to do the method of undetermined coefficients via the superposition approach, or even trying to find the solution to a homogeneous equation with constant coefficients, we need the auxiliary equation. And if you look at this differential equation, the auxiliary equation for the dE is 2m squared minus 3m minus 2 equals 0. And if you closely observe, that and that are one and the same. We simply replace the m by d. So if you connect the dots, you can see that they are closely related. Here we have a third order differential equation, and we would want to write it it simply wants us to write the given differential equation of the form I feel like I'm missing something in this question. It's in the form, not of the form. Okay, the annihilation part is coming later on, so we just want to write the differential operator. So this is a third order differential equation, so I could write this as d cubed y plus 4d squared y plus 3d y equals x squared cosine 3x minus 3x. If I pull y out, I have d cubed plus 4d squared plus 3d y equals x squared cosine 3x minus 3x. I have a d in common, so I have d squared plus 4d plus 3y equals x squared cosine 3x minus 3x. I can factor d squared plus 4d plus 3 as d plus 1 times d plus 3, y equals x squared cosine 3x minus 3x. So L of y is d times d plus 1 times d plus 3, y, and g of x is x squared cosine 3x minus 3x. Here we have a case where we have a fourth order differential equation. So I could write the fourth derivative as d raised 4y minus 8d squared y plus 16y equals x cubed minus 2x e raised 4x. I could pull the y out, d raised 4 minus 8d squared plus 16 times y equals x cubed minus 2x e raised 4x. Could we factor this? I believe we can. This is simply d squared minus 4 squared So we will have d squared minus 4 times d squared minus 4 times y equals x cubed minus 2x e raised 4x. So L of y is d squared minus 4 times d squared minus 4 times y, and g of x is x cubed minus 2x e raised 4x. Now we want to verify if the differential operator annihilates the indicated functions. Now we know d raised 4 will annihilate any polynomial of degree less than or equal to 3. So it has to get rid of x cubed, it will get rid of x. So let's see if it works. So d raised 4 of 10x cubed minus 2x would equal 10 d raised 4 x cubed minus 2 dx. So 10, the fourth derivative, d raised 4 is simply d times d times d times d. So I could write it as d cubed. First derivative of x cubed is 3x squared. Derivative of x is, that's d raised 4, sorry. 1. Apply the derivative again, I'll have 6x. The derivative of 1 is 0. You can see I'm reducing the powers of the differential operator. I can ignore the second term now. Derivative, one more time, would be 6. And the derivative of 6 is 0. So clearly, d raised 4 annihilates 10x cubed minus 2x. So we'd like to see if d squared plus 64 would annihilate that giant expression. So d squared plus 64 applied to y, which is 2 cosine 8x minus 5 sine 8x. That would equal to d squared applied to 2 cosine 8x minus 5 sine 8x plus 64 times 2 cosine 8x minus 5 sine 8x. The first term I could write it as d of d times d is d squared, 2 cosine 8x minus 5 sine 8x. Distribute, we would have 128 cosine 8x minus 320 sine 8x. The 2 can come out because it is a constant, so we are applying the differential operator here, so 2 operator applied to 8 cosine 8x minus 5 operator applied to sine 8x plus 128 cosine 8x minus 320 sine 8x. The derivative of cosine 8x is negative 8 sine 8x. Derivative of sine 8x is 8 cosine 8x. So negative 16 sine 8x, negative 40 cosine 8x, plus 128 cosine 8x, minus 320 sine 8x. Apply the derivative operator to this expression, so we will have negative 16. Derivative operator applied to sine 8x, minus 40, derivative operator applied to cosine 8x, so we would get negative 16 times 8 cosine 8x, negative 40, negative 8 sine 8x, plus 128 cosine 8x, minus 320 sine 8x. So we have negative 128 cosine 8x, plus 320 sine 8x, plus 128 cosine 8x, minus 320 sine 8x equals 0. Because they would simply get cancelled. So clearly d squared plus 64 annihilates y equals 2 cosine 8x minus 5 sine 8x. We know that d minus alpha will annihilate exponential, so we have d minus 2 and d plus 5, and we want to see if it would annihilate e raised to x plus 3 e raised minus 5x. So first step is we can either do it by foiling and then applying the operators, or keep the factors and as is, and then apply one factor at a time. So I'm going to use the latter approach. So d minus 2 times d plus 5 applied to e raised to x plus 3 e raised minus 5x. So d minus 2 applied to d plus 5 multiplied by e raised to x plus 3 e raised minus 5x. D minus 2. The derivative operator applied to e raised to x plus 3 e raised minus 5x plus 5 e raised to x plus 3 e raised minus 5x. The derivative of e raised to x is 2 e raised to x. Derivative of 3 e raised minus 5x is negative 15 e raised minus 5x. I'm going to add or distribute the 5. So I'll have 5 e raised to x plus 15 e raised minus 5x. Those two would go away, and we will have d minus 2, 2 e raised to x plus 5 e raised to x, that is 7 e raised to x. Clearly, d plus 5 got rid of e raised minus 5x. We don't see it over there. It is gone. Now, naturally, d minus 2 is going to get rid of that e raised to x. So 7 comes out. I have d minus 2 e raised to x. So 7 d e raised to x minus 2 e raised to x. Derivative of e raised to x is 2 e raised to x minus 2 e raised to x. That is 7 times 0, 0. So d minus 2 times d plus 5 annihilates y equals e raised to x plus 3 e raised minus 5x. So now we have a combination of an exponential and an algebraic function. So we have d squared minus 2d plus 1. It's better to factor this. If we factor d squared minus 2d plus 1, we would simply have d minus 1 times d minus 1. So I'm going to apply d minus 1 times d minus 1 to e raised x plus x e raised x. So that would equal to d minus 1. Writing it in factors is beneficial because we know a standard form that is going to get rid of an exponential. So in this case, I know d minus 1 would take out e raised x. So it would sort of help us getting rid of terms right away, which is why I like to do it one factor at a time. So d minus 1 e raised x plus d minus 1 x e raised x. We know d minus 1 will annihilate e raised x, so that goes away. D minus 1 d applied to x e raised x minus x e raised x. The derivative of x e raised x, if we use product rule, it is simply x e raised x plus e raised x. So we will have d minus 1 x e raised x plus e raised x minus x e raised x. Those two would go away. And I have d minus 1 e raised x. But we know d minus 1 will annihilate e raised x from the previous problem. We can verify it if we want. D applied to e raised x minus e raised x, it's e raised x minus e raised x, we get 0. Looks like that is a repetition that shouldn't be there. Okay, in the previous examples we had an expression and we tried to find, we had an operator, we applied the operator, we ended up getting or verifying if the operator annihilated the expression. Here all we have is an expression and we want to find an operator that would annihilate that function. So I look at that polynomial, that is a polynomial, so I look at the highest power, which is 3. So that would tell me d raised 4 will annihilate y. Let's see if it's true. So d raised 4, 1 plus 6x minus 2x cubed equals d raised 4 of 1, d raised 4 of 6x minus d raised 4 of 2x cubed. Fourth derivative of 1 is 0. I could write this as d cubed or 6d cubed d of x minus 2d cubed d of x cubed. D times d cubed is d raised 4. The first derivative of x is 1 minus 2d cubed. Derivative of x cubed is 3x squared. I could write d cubed as d squared, d of 1, minus 2d squared. We could pull that 3 out and write it as 6. Derivative of 1 is 0, 6d squared times 0, minus 6d squared times the derivative of x squared. I get 2x. So bring the 2 out. D squared x. So we would have negative 12 d of x. Negative 12. Derivative of x is 1. And negative 12 derivative of 1 is 0. We get 0. So clearly d raised 4 will annihilate the entire expression 1 plus 6x minus 2x cubed, because d raised 4 would annihilate all expressions all the way up to x cubed. So I should probably put that as a remark. So if we have an expression, we had 1x, x squared, x cubed multiplied by constants, every single one of them will be gotten rid of by d raised 4. So here we have a constant and we have sine x, and we want to come up with an operator that would get rid of 1 plus sine x. So we know d squared plus beta squared annihilates sine beta x. We know that. What would annihilate 1? d would annihilate the constant. So, by looking at it, d squared plus 1 annihilates sine x, because beta is 1, and d will annihilate 1. Now, should we add, should we multiply? We have to multiply. So this would imply d times d squared plus 1 will annihilate 1 plus sine x. We can quickly verify this. Once we get used to it, you don't have to verify, you just know. So d squared plus 1 apply to 1 plus sine x, d squared plus 1 apply to 1 plus sine x. So d squared apply to 1 plus sine x, and we have 1 plus sine x. I'm distributing. So d squared of 1 plus d squared sine x plus 1 plus sine x, d 0, d of sine x plus 1 plus sine x. The derivative of sine x is cosine x. So d of cosine x plus 1 plus sine x. The derivative of cosine x is negative sine x. The sine x would go away. We'll have d of 1, derivative of 1 is 0. So if we have a linear combination of multiple functions, different functions, we simply find the annihilators for each of them and multiply them to get rid of the linear combination of functions. That is the point of this exercise, because linear combinations are very, very important when it comes to differential equations. Okay, so here we have three functions, 8x minus sine x, 10 cosine 5x. These constants typically don't matter. What matters is the form of the function. So since we have x, d squared will annihilate x. Observation 1. Observation 2, d squared plus 1 will annihilate sine x, because we know d squared plus beta squared annihilates sine beta x from the previous problem right there. So I would want you to know this clearly, the key expressions. If you don't forget these, then you can easily do problems of this sort. Lastly, we have cosine 5x. Beta is 5 in this case, so it should be d squared plus 5 squared will annihilate cosine 5x. This would mean d squared times d squared plus 1 times d squared plus 25 will annihilate 8x minus sine x plus 10 cosine 5x. You don't have to verify. I am very confident that this is going to work out, but if you have the time, you can verify. So now we have a linear combination of exponentials, algebraic functions, and exponentials. A whole bunch of things going on here. So first, we've got to look at e raised negative x. So alpha here is 1. So d minus of minus 1 will annihilate e raised minus x. Great. Which would mean the operator is d plus 1. We have x e raised x. So alpha is 1 in the exponent. And there is an x in the front. So d minus alpha or squared, will annihilate x e raised x. Y I see x raised 1 and e raised 1 times x. Alpha 1. I see 1 there, hence 2. And lastly, I have x squared e raised x. So d minus 1 raised 3 will annihilate x squared e raised x. I see 1 there, that is alpha, hence 1 there. Power is 2, so d cubed will annihilate x squared, hence d minus 1 cubed will annihilate x squared times e raised x. So the operator is d plus 1, d minus 1 squared times d minus 1 cubed, which is d plus 1, times d minus 1 raised 5 will annihilate e raised minus x plus 2x e raised x minus x squared e raised x. If you attempt to verify this, go ahead. It is going to be a lengthy process, but it is certainly doable. So now we want to find a, shouldn't be there. Okay. We have to find linearly independent functions that are annihilated by the given differential operator. I spelled differential wrong. I've noticed it earlier, but it's all right. D raised 5. We know D raised 5 annihilates 1 x, x squared, x cubed, x raised 4. So we want to find linearly independent functions that are annihilated by that differential operator. So those are the linearly independent functions. So any combination of these linearly independent functions would also be annihilated. So consider f of x equals c1 plus c2x plus c3x squared plus c4x cubed plus c5x raised 4, then f of x will be annihilated by d raised 5. It is a given. So now here we want to find a set of linearly independent functions that are annihilated by the differential operator d squared plus 4d. First step is to identify, first step is to factor. So I have d squared plus 4d. If I pull d out, I have d plus 4. I know that I could write d plus 4 as d minus 4. So if we note d minus alpha annihilates e raised alpha x, so d plus 4 annihilates e raised minus 4x, and d annihilates a constant term, I'll just say 1, and that's it. So any function of the form c1 times 1 plus c2 times e raised minus 4x will be annihilated by d squared plus 4d. It is the same as saying d times d plus 4. So here we have d squared times d minus 5 times d minus 7. So we know d minus alpha annihilates e raised alpha x. So I have two alphas, one is 7, other is 5. So d minus 5 will annihilate e raised 5x. D minus 7 annihilates e raised 7x. D squared annihilates expressions of the sort 1, x, and that's it. It can't go up to x squared, so 1 and x. So any linear combination, so any function of the form y equals c1 times 1, c2 times x, c3 times e raised 5x, c4 times e raised 7x will be annihilated by d squared times d minus 5 times d minus 7. So now we have d squared minus 6d plus 10. Things aren't obvious just by looking at it. This is where factoring comes into play. So is it possible to factor? Well, minus 6d and 10. Well, looks like. Probably not. So if we write it as a quadratic function, we have minus b plus or minus square root of b squared minus 4 times a times c divided by 2 times a, which is 1. So 36 plus or minus square root of 36 minus 40, oops, bad algebra, 6 divided by 2, 6 plus or minus square root of negative 4 divided by 2, 6 plus or minus 2i divided by 2, 3 plus or minus I. So we'd have 3 plus I and 3 minus I. Going back to solving homogeneous equations with constant coefficients, if we have an auxiliary equation with complex conjugate pairs as roots, then the solution that we write has an exponential part and a cosine and the sine part. So recall, in the auxiliary equation form, I could write this as 6m squared minus m plus 10. So I can infer that alpha is 3 and beta is 1. So d squared minus 6d plus 10 will annihilate e raised 3x cosine beta x, which is 1x, and e raised 3x sine beta x, which is 1 times x, which is 1. Another way to find it, we know that d squared minus 2 alpha d plus alpha squared plus beta squared annihilates e raised alpha x cosine beta x and e raised alpha x sine beta x. So by direct comparison, minus 2 alpha, or 2 alpha, would equal 6, and alpha squared plus beta squared would equal 10. Alpha is 3, and 3 squared plus beta squared equals 10. Beta squared equals 10 minus 9. Beta is plus or minus 1. And we just keep the positive value. So, what we have here and what we have there are one and the same. So it's entirely up to you, but this general form is quite useful in identifying the linearly independent functions right away. So the linearly independent functions are those two. Also, any function of the form y equals c1 e raised 3x cosine x plus c2 e raised 3x sine x will be annihilated by d squared minus 6d plus 10. So, key to identifying annihilator operators is right here. It's the most important part of the annihilator approach. You've got to understand this, and the objective is to use the annihilator operator to convert a non-homogeneous equation to a homogeneous equation so we could find the solution right away. And this is an alternative to the superposition approach. So we are going to solve this differential equation using the Annihilator approach. So what we have is y double prime minus 9y equals 54, which I could rewrite it as d squared minus 9 multiplied by y. The reason being y double prime is d squared y minus 9y equals 54, and I simply pulled out the y to get d squared minus 9. So that would give us d plus 3 times d minus 3 y equals 54. And what would annihilate 54? So if I apply d on both sides, d will annihilate 54 because it is a constant. So I have d times d plus 3 times d minus 3 y equals d of 54. That would simply be 0, and d plus 3 and d minus 3 y. Now what we started with is a non-homogeneous equation. And now, after applying, we ended up getting a homogeneous equation. Applying the differential operator, I mean. So we know the auxiliary equation comes from that part. If you can't see it right away, you can actually write based on what we've learned earlier for homogeneous equations, the auxiliary equation corresponding to y double prime minus 9 is simply m squared minus 9 equals 0. So the two roots of the auxiliary equation are m1 equals 3 and m2 equals minus 3. So I'm just setting, d plus 3 equals 0, d minus 3 equals 0. I end up getting the two roots. So the complementary solution is yc equals c1 e raised 3x plus c2 e raised minus 3x. Now we have to find the particular solution. This is where the annihilator approach comes handy. So I could write the homogeneous equation after annihilation as d minus 0, d plus 3, times d minus 3, y equals 0. So now I'm going to look at that part, and I know the root of that is simply, I'll call it m4 or m3. Is simply 0. So the form of the particular solution is yp equals some constant c3 e raised 0x, which is simply c3. So that would imply yp prime equals 0, yp double prime is also equal to 0. We can take these values and plug in yp prime and yp double prime, actually yp double prime and yp in the original differential equation, so we would end up having 0 minus 9 times c3 equals 54, which would imply negative 9c3 equals 54, c3 equals negative 6. So the particular solution is simply yp equals negative 6. So the solution to the DE is YC equals C1 e raised 3x plus C2 e raised minus 3x minus 6. And as always, the particular solution doesn't have any arbitrary constants. So now we have a second order differential equation, and the right hand side g of x is a linear function, and it is of the form 4x minus 5. So first I can rewrite the differential equation using the differential operator. So d squared plus d y equals 4x minus 5. Now that would simply imply the auxiliary equation is m squared plus m equals 0, which would mean I'm directly guessing that from here. Now, the auxiliary equation is for a homogeneous equation, and you may say, well, this is a non-homogeneous equation, and why is he doing it right now? I like to do it at this step so that I don't get confused with the differential operators that I apply later on. Because I know eventually I'm going to make this non-homogeneous equation or turn this non-homogeneous equation into a homogeneous equation. So I'm not worried about rewriting d squared plus d as m squared plus m. So I have m times m plus 1 equals 0, which would imply m is 0 and m plus 1 equals 0. So I have m to be 0 and m to be minus 1. So the complementary function or solution is y equals c1 e raised m1x plus c2 e raised m2x. So c1 e raised 0 times x plus c2 e raised minus 1 times x. So I have c1 plus c2 e raised minus x. Now going back to the homogeneous equation, or non-homogeneous equation, and I'm going to apply an annihilator that would get rid of 4x minus 5. And we know the annihilator operator corresponding to 4x minus 5 is d squared. So d squared times d squared plus d equals 4x minus 5, and I'm going to apply d squared to it. Which would make the right-hand side 0. So I already found the roots for the auxiliary part, which would be that part, so I'm not worried about that. I need the form of a particular solution, so I have d minus 0 times d minus 0 times d squared plus d equals 0. So the two new roots are m3 equals 0 and m4 equals 0. Now keep in mind, these are repeating roots. We already had m1 equals 0 earlier, so we've got to be careful when we write the particular solution. So the particular solution is of the form yp, since we have repeating roots, c3 e raised 0x times x, c4 e raised 0x times x squared. So yp is x c3 times x plus c4 times x squared. This would mean yp prime is c3 plus 2c4x, and yp double prime is simply 2c4. We plug in yp double prime and yp prime in the given differential equation, which is yp double prime 3y prime 3yp prime equals 4x minus 5. So we have 2c4 multiplied by 3 times c3 plus 2c4x. That would be equal to 4x minus 5. So we have 2c4 plus 3c3 plus 6c4x equals 4x minus 5. Now we could use superposition approach to evaluate c4 and c3. 6c4 equals 4, and 2c4 plus 3c3 would equal negative 5. Which would mean c4 is 2 over 3. 2c4 plus 3c3 equals negative 5. So 2 times 2 over 3 plus 3c3 equals negative 5. Which would mean 4 over 3 plus 3c3 would equal to negative 5. So 3c3 would equal to negative 5, negative 4 over 3. 3c3 would equal negative 19 over 3. c3 would be negative 19 over 9. So we've found c4, which is 2 over 3, and c3, which is negative 19 over 9. So plug it in the equation. So we would have yp equals 2 over 3x squared minus 19 over 9x. So that is the particular solution. Therefore, the solution to the dE is y equals c1 plus c2 e raised minus 3x plus 2 over 3x squared minus 19 over 9x. So we have a second order non-homogeneous equation, and I'm going to rewrite it in terms of the differential operator, d squared y minus dy minus 12y equals e raised 4x. I could pull the y out, d squared minus d minus 12 times y equals e raised 4x. And now the auxiliary equation is m squared minus m minus 12 equals 0. And I can easily factor this as m minus 4 times m plus 3 equals 0. So the roots are m1 equals 4 and m2 equals 3. So the general solution is, oh sorry, I meant to say complementary. The complementary solution is y equals c1 e raised 4x plus c2 e raised negative 3x. Bad algebra. Now we can move on and find the particular solution. For that, we've got to know what would annihilate e raised 4x. We know d minus 4 annihilates e raised 4x. So this would imply I'm going to multiply the differential equation on both sides by d minus 4, which would make the right-hand side 0. The root for the particular solution is obtained using d minus 4. So here we will have m3 equals positive 4. But keep in mind, we already have m1 equals 4. So the particular solution is of the form yp equals c3 x e raised 4x, because we already have a root that equals 4. We could find the first derivative, second derivative, and plug it in. Yp prime is c3 4x e raised 4x plus e raised 4x times 1. And that would give us 4c3 x e raised 4x plus c3 e raised 4x. Yp double prime would be equal to 4c3 4x e raised 4x plus e raised 4x. That would give us 16c3 x e raised 4x plus 4c3 e raised 4x. And there is a c3 e raised 4x outside, and if I take the derivative of that, I would have 4c3 e raised 4x. So I end up getting 16c3 x e raised 4x plus 8c3 e raised 4x. Plug all of this in the original equation, so plug in yp double prime, yp prime, and yp in yp double prime minus yp prime minus 12yp. That would equal e raised 4x. Yp double prime is 16c3x e raised 4x plus 8c3 e raised 4x. Now, we don't want the x e raised 4x term because I don't see any x e raised 4x on the other side. So I'm going to keep things simple. I'm going to gather only the e raised 4x terms. So I'll take that from the second derivative. I'll take that from the first derivative and ignore the yp part because it has x e raised 4x. So I would have negative or positive 8c3 e raised 4x minus c3 e raised 4x. That would equal e raised 4x. This would mean 7c3 is equal to e raised 4x. c3 is equal to 1 over 7. So 7c3 is actually equal to 1. So plug in yp, so the particular solution is yp equals 1 over 3 x e raised 4x. So the general solution is y equals c1 e raised 4x, c2 e raised minus 3x, plus 1 over 7 x e raised 4x. So here is a second order DE with trigonometric functions. So I'm going to rewrite it in terms of differential operators. So d squared y plus 4 times y equals 4 cosine x plus 3 sine x minus 8, which would mean d squared plus 4 times y equals 4 cosine x plus 3 sine x minus 8. The auxiliary equation is m squared plus 4 equals 0, which would imply m squared is equal to minus 4, so m is plus or minus 2i. So root 1 is 2i, root 2 is minus 2i, so alpha is 0, beta is 2. The complementary solution is y equals c1 cosine 2x plus c2 sine 2x. Now we have to find the particular solution. We know that d squared minus 2 alpha d plus alpha squared plus beta squared annihilates cosine x as well as sine x. But there is a constant term, minus 8. We've got to get rid of that too. Sorry, this should be cosine beta x. Sine beta x, e raised alpha x, e raised alpha x. In our case, alpha is 0, and beta is 2. This would mean d squared plus 4 will annihilate oh, it's not 2, it's actually 1. Because we have to annihilate cosine x and sine x, and beta is 1 there, so this should be d squared plus 1. But we have a constant 8, we've got to get rid of that too, so d will annihilate the negative 8. So we have to multiply both sides by d times d squared plus 1 times d squared plus 4 times y equals d times d squared plus 1, the right hand side, 4 cosine x plus 3 sine x minus 8. And that would become 0 because d times d squared plus 1 will annihilate the right hand side. So I could write d minus 0, d squared plus 1, d squared plus 4 times y equals 0. The roots for the particular solution are m3 equals 0, m4 and m5. We can get that from setting that equal to 0, which would mean m squared plus 1 equals 0, m squared equals minus 1, m is equal to plus or minus I. So m4 is 1, I, so I'll just put it as I, and m5 is minus I. So the particular solution is of the form yp equals c3 e raised 0x, c4, beta here is 1, alpha is 0. This is for the particular solution. Don't confuse it with the complementary solution. So I would have c4 cosine x plus c5 sine x. So the particular solution is of the form c3 plus c4 cosine x plus c5 sine x. Now we have to find the first derivative. So yp prime is c4 negative c4 sine x plus c5 cosine x. Yp double prime is negative c4 cosine x, negative c5 sine x. We plug in yp double prime and yp prime in the original DE, which is y double prime plus 4y equals 4 cosine x plus 3 sine x minus 8. Yes. So we would have to gather all the cosine terms, so negative c4 cosine x, negative c5 sine x, plus 4 times y prime, or it's actually y, so 4 times y, which is c3 plus c4 cosine x, plus c5 sine x equals 4 cosine x plus 3 sine x minus 8. So if we combine the terms, we would end up getting 3 c4 cosine x plus 4, actually, 3 c5 sine x plus 4 c3 equals 4 cosine x plus 3 sine x minus 8. By direct comparison, we could see 3c4 equals 4, 3c5 equals 3, 4 equals, or c3 equals or 4c3 equals minus 8. So 3c4 equals 4, which would imply c4 equals 4 over 3. 3c5 equals 3, which would imply c5 is 1. 4c3 equals minus 8, it would imply c3 is minus 2. Take that and plug it in yp. So yp would be minus 2 plus 4 over 3 cosine x plus 1 times sine x. So the general solution is y equals c1 cosine 2x from earlier, c2 sine 2x, plus 4 over 3 cosine x plus sine x minus 2. Here we have a third order differential equation, and I'm going to rewrite it in terms of the differential operators. So d cubed y minus 3d squared y plus 3dy minus y equals e raised x minus x plus 16. So d cubed minus 3d squared plus 3d minus 1 multiplied by y equals e raised x minus x plus 16. The corresponding auxiliary equation is m cubed minus 3m squared plus 3m minus 1 equals 0. That would mean m minus 1 cubed would equal 0. So the roots are m1 equals 1, m2 equals 1, and m3 equals 1. So the complementary solution is y equals c1 e raised 1 times x plus c2, these are repeating roots, x times e raised 1 times x, c3 x squared e raised 1 times x. So y is c1 e raised x plus c2 x e raised x plus c3 x squared e raised x. Now we have to find the particular solution. We see e raised x term, and a 16. We know that d minus 1 annihilates e raised x. D squared annihilates x. And d annihilates 16. So we multiply both sides. So we already have d1 cubed. So we multiply it by d times d squared times d minus 1 on both sides. Which would make the right-hand side 0. We have accounted for that part already, so the roots for the particular solution are d equals 0, d squared equals 0, and d minus 1 equals 0. So I'm taking those three to get those. And that would mean M4 is 0, M5 is 0, M6 is 0, M7 is 1. And we already have an x term, x squared term, so we need to have repeating roots here. So the x term, the d minus 1 would apply for e raised x. Its root is 1. The d squared term applies for the x term, and the d would apply for the term 16. So we would end up having the particular form it's actually excuse me, I made a mistake here. D squared would actually annihilate both x and 16 because it is d squared. If you take the second derivative of 16, it will become 0. So we don't need that d term. So I'm going to get rid of that d. So I would simply have d squared times d minus 1. So we don't need as many roots. So we would have d squared equals 0 and d minus 1 equals 0. So M4 is 0, M5 is 0, and M6 is 1. We already have one root that would be replicated, which is M6 equals 1. And here we have two repeating roots. So the form of the particular solution would be C4 e raised 0x plus C5 x e raised 0x plus C6. M6 is a repeating root, so x e raised 1 times x, because we already have, we actually have constant x and x squared, so this has to be x cubed. So the particular solutions form is C4 C5x plus C6 x cubed e raised x. Now we have to find the third derivative, second, first, and yp. So the first derivative is C5 plus C6. 3x squared e raised x plus x cubed e raised x. The second derivative is c6 e raised x multiplied by 6x plus 3x squared plus c6 multiplied by 3x squared plus x cubed times e raised x. Using product rule here, so which would mean c6 e raised x multiplied by x cubed plus 6x squared plus 6x. Yp triple prime is c6 e raised x multiplied by 3x squared plus 12x plus 6 x cubed plus 6x squared plus 6x multiplied by c6 e raised x. Which I could write it as c6 e raised x multiplied by x cubed plus 9x squared plus 18x plus 6. We take all that and plug it in the original DE. So plug in yp triple prime, yp double prime, yp prime, and yp in yp triple prime minus 3 yp double prime plus 3 yp prime minus yp equals e raised x minus x, I believe it was 16, so minus 16. Oh, plus 16. So all I need is e raised x term and the x term and 16. So let's see if we can gather. This is the shortcut. So the e raised x terms, I have 6 c6 e raised 6 from the third derivative. From the second derivative, I don't need any e raised x terms. First derivative, nothing that I can see of. And yp, nothing. Second derivative, I need an e raised x term or an x term. The third derivative has no x terms. Okay. And the second derivative, I'm looking for e raised x or a constant. I don't see any e raised x terms, so I'm going to leave it as is. First derivative, I need e raised x. I see a constant, I have a constant, so I've got to put that in. So c5. In yp, I have c4. I have c5, I have an x term. And I have x cubed e raised x, so I don't need that. And that should equal e raised x minus x plus 16. So I would end up getting 6c6 e raised x plus 3c5 minus c4 minus c5x equals e raised x minus x plus 16. By direct comparison, I could see 6c6 is equal to 1. 3c5 minus c4 equals negative 1. And negative c5 is equal to 16. which would imply C5 is negative 16. Now that we've found C5, we could actually find the other numbers. So we have C6 to be 1 over 6, 3, oh, sorry, this C5 plus C4 wasn't as easy I thought it would be. Minus C4 feel like I'm missing a term. So erase x, when I gather, I have 6. In the second derivative, I only have those terms. In the first derivative, I have those terms. Okay. I know where I went wrong. Negative C5x equals erase x minus x plus 16. I just compared the wrong terms. So negative C5 would equal negative 1, comparing that to that. And I would have 3C5 minus C4 equals 16, which would imply C5 is 1. 3 times 1 minus C4 is equal to 16, which should imply minus C4 equals 16 minus 3. Minus C4 is equal to 13. C4 is minus 13. Now that we have C4, C5, and C6, the particular solution is minus 13 plus C5 is 1. 1 times x is x, plus 1 over 6 x cubed erase x. And the general solution is y equals yc plus yp. Yc is c1 erase x, c2 x erase x, c3 x squared erase x, 1 over 6 x cubed erase x, plus x minus 13. I could pull erase x out and write it as c1 plus c2x plus c3x squared plus 1 over 6x cubed plus x minus 13. And that would be the solution. Here is an initial value problem that we are going to solve using the Annihilator approach. I'm going to rewrite the differential equation as d squared y plus 5dy minus 6y equals 10 e raised to x. If I pull the y out, I have d squared plus 5d minus 6y equals 10 e raised to x. So the auxiliary equation is simply m squared plus 5m minus 6 equals 0, which would mean I would have m plus 6 times m minus 1 as the factors. So the two roots are m1 equals minus 6 and m2 equals 1. The general solution is y equals c1 e raised minus 6x plus c2 e raised x. Now that we have the general solution, we want to look for the particular solution. We can identify the form of the particular solution by determining the operator that would annihilate e raised to x. We know d minus 2 annihilates e raised to x. So I'm going to multiply both sides of the differential equation by d minus 2. So d plus 6 times d minus 1y equals d minus 2 e raised to x. The right-hand side would become 0. D minus 2 times d plus 6, d minus 1 times y. And that would give us the root for the particular solution. So the root in this case is m minus 2 equals 0, which would imply m3 is 2. So the form of the particular solution is yp equals c3 e raised m3, which is 2x. Now we've got to find the first derivative of yp. Yp double prime is 2c3 e raised to x. Yp prime is 2c3 e raised to x. Yp double prime is 4c3 e raised to x. Plug in yp double prime, yp prime, and yp in yp double prime plus 5 yp prime minus 6 yp equals 10 e raised to x. So we have 4c3 e raised to x plus 5 times 2c3 e raised to x minus 6 c3 e raised to x equals 10 e raised to x. That would give us 8c3 e raised to x equals 10 e raised to x, giving us c3 to be 10 over 8, which is 5 over 4. So the particular solution is yp equals 5 over 4 e raised to x. Therefore, the general solution is y equals c1 e raised negative 6x plus c2 e raised x plus 5 over 4 e raised to x. Now we've got to find the constants. Y of 0 is 1, y prime of 0 is 1, y prime is negative 6c1 e raised minus 6x plus c2 e raised x plus 5 over 4 2 e raised to x. Y of 0 is equal to 1. So plug in 0, I will get c1 plus c2 plus 5 over 4, which would mean 1 minus 5 over 4 is equal to c1 plus c2. So c1 plus c2 is negative 1 over 4. Y prime of 0 is also 1. So negative 6c1 plus c2 plus 5 over 2 would equal 1. So we have 1 minus 5 over 2 equals negative 6c1 plus c2. So negative 6c1 plus c2 equals negative 3 over 2. So the two equations are c1 plus c2 equals negative 1 over 4. Negative 6c1 plus c2 is negative 3 over 2. We subtract them. 7c1 would be equal to negative 1 over 4 plus 3 over 2. We need a common denominator, so we would have negative 2 over 8 plus 12 over 8, which should be 10 over 8. That is 5 over 4. So 7c1 is 5 over 4. c1 is 5 over 28. We'll take that and plug it in c2. In the first equation, c1 plus c2 is minus 1 over 4, which would imply c2 plus 5 over 28 equals minus 1 over 4. c2 would equal to minus 1 over 4 minus 5 over 28, and that would give us negative 7 over 28 minus 5 over 28 minus 12 over 28, and that is negative 3 over 7. So we have c1 and c2, therefore the general solution satisfying the initial conditions is y equals 5 over 28 e raised negative 6x, negative 3 over 7 e raised x, the first two terms, and the last term is the particular solution, plus 5 over 4 e raised to x.